in the grid. And the common denominator of all this equipment is that we have to insulate the high voltage in some way, different way. So electrical insulation always is the thing. Just to show some exotic things as well, I like that, although this is DC. We use HVDC on satellite transmitters in space. You know, there are many satellites that take care of communication, yeah. And there would not be a lot on television if all the satellites didn't function all of a sudden. Yeah. If I tell you that in these satellites you have high voltage equipment in all of them, and they are called, these things are called traveling wave tubes. Anybody? I see one yes, but I guess most of you don't know what it is. I'm not going to tell you, but it's an amplifier. It's an ultra wideband microwave amplifier. Maybe 6-7 decades of amplification without introducing noise, and you need high voltage for that. Isn't that nice? If you want to know more about that, you go to the high voltage DC lectures, but that's in the 4th quarter. That's something you wouldn't expect, I guess. Also in medical applications, X-ray. In order to produce X-ray, we still need high voltage. Up to larger than 100 kilovolt DC again. So we also have many challenges there because everything needs to become smaller and smaller, because in the hospital or at your dentist they don't care about high voltage, they care about making the photograph. Yeah? So they don't want to have high voltage transformers and everything lying around there, so it should become more and more compact. As things become more and more compact, if the voltage remains the same, the electric field goes up. And high electric field is a challenge, so there you are. Testing of high voltage components really is the topic of the next series of lectures. And Anna, the lecturer, is here. He's maybe you can show yourself just for a second, Armando. Sorry for that, I didn't have one. That's Armando Rodrigo, and he's going to take care in the second semester the lectures of let's say high voltage testing and so on, and measurements. Yeah. We can have very exotic testing. And you can see that the ice. Yeah. So luckily here in the Netherlands, I don't know how far the climate is going to change, but right now we don't have to worry about that. But some countries that do need to worry about that. Canada, Russia, yeah. And so we have this growth of ice. Do you think that this is a problem? Be careful when I put it like this. The situation that we see here, ice on the insulators and everything, is that a problem?
It is.
Could damage the ceramics maybe?
Also,
Why is it
they're
just
changing
like
the
this?
field.
No.
They're changing the field.
Will change
it
the field? Maybe. Not so much maybe. What do you know about ice?
It's conducting.
Sorry? Conducting?
Maybe on the surface of ice there is some conduction, but I think the big problem is that you can damage the insulation thanks to the changes of length in the material. But you get also in railways.
What about
there is
mechanical
some
damage?
movement of the material.
There's a lot to be said about this thing. I'm not saying you're wrong, but that is not the biggest issue. In fact, mechanical damage, you say,
Due to weight.
maybe, but well, I don't care about that. I only care about electrical damage here. And what we know, ice is water, but then all the properties of water seem to have changed when you go from water in a liquid state to ice. Ice is what we call crystalline. Look at the ice crystals. Yeah. We know about most these crystalline materials that have a very high resistivity. You can consider them to be insulators. So this is just like insulating peaks hanging there. Yeah. And no, I won't go too much in detail. So this is not the worst thing, but it will not always look like this. Even in Canada and in Russia, at some point in time, we will have spring. What happens then? Why is spring a problem?
Ice melts.
The ice melts, yeah. And then at the surface we have water, and not pure distilled water probably, but cannot be all kinds of polluting substances. So the water is conducting. So we have our nice post insulators with conducting paths running there. So if something is going wrong, it's in spring when the ice starts to melt. But so this is the way I want you to approach things, understand, yeah? And not just remember, okay, in spring there's a problem because then ice becomes water, but then I would ask you, but why is that a problem then? Yeah? Okay, this is the way I work. So we need to test for these situations, so not we here, but in Canada and so. Yeah. At the same time, we need to test for other conditions, high altitude conditions. There's also in China special test base and test systems to see what is the flashover voltage of large constructions at high altitude. Because what is so different at high altitude? Pressure, yeah. Okay, there you go. So, about the course now, this is a very long introduction, but at least gives you a bit of a picture now about the book and the contents. It is divided in 3 parts. There's some logic behind. First part is fields and then electric fields. So it's partially a revisit of things you should have already learned in your bachelor. Don't worry too much. It's all about electric field. You don't see voltage there, huh? It's electric field. I will explain in a later stage why we care so much about the electric field and not the voltage, because I guess by now you can just copy me and saying that the electric field is important, because I told you a few times now, but do you know why? I don't think so. So, but I will tell you later. This is one of the things I expect you to ask me. You say all the time, it's electric field, and you never ask me why, to explain why. Okay, now you don't have to, because now I told you I will explain that. Then, in the second part, we'll focus on insulating materials, or dielectrics, and more in general, how do they break down? How do they fail? What is necessary to fail? So we start with nothing, vacuum. It's not really a material, of course, it's a lack of material. So you will learn how a breakdown is triggered in vacuum constructions. Then we increase the pressure, we go to gases at low pressure. Then here. There's no lights burning now, but these lights there, these are really breakdowns or discharges at low pressure. Yeah. And one of the things you will learn is that these gases shouldn't break down here when we apply voltage of 230 volts. But still they do, because there is light. Yeah. I'm quite sure you never wondered about these things. Just consider it to be a light bulb. Yeah. But I'm going to explain you why first why it shouldn't work, and then why it does work. Okay. It's a good thing. So then a sidestep to lightning. Lightning, of course, is not an insulating material, but lightning, we have gas at what we call at high pressure, ambient air. It's a very special thing. Then we go further in the row, we're going to make the gas thicker, and then we get to a liquid. Oil, for instance. And even thicker, we get to solids. So for the whole range of possible insulating media, I will teach you how the breakdown mechanism takes place. This is what you need to know in order to avoid breakdown taking place. But this is all for single materials. And as I already told you before the break, in the end, in practice, we never deal with one single material. We deal with the name of the course constructions. So then we focus on real things that get much closer to real applications constructions, and how that affects the behavior. And part of what you need, if suppose you're a designer of some high voltage component, you need to have a toolbox. You make a design, you make some calculations, you're not satisfied with it for some reason, and then you need tools to reshape the insulated construction in such a way that you get what you want. And this is what we call field grading. You can shape the electric field in a way that allows us to get a lifetime of 30 years using that particular construction in that field. And that's the end of the course. Then. It's always not. I hate it when somebody presents something and then is looking at his own or her own sheet and is surprised. This is happening to me now because I see some operators here. I don't know why it looks like this. Probably because I have a new version installed of Microsoft PowerPoint. It's always good to blame Microsoft, isn't it? So, anyway, maybe you can help me figuring out what are the correct parameters and operators here. So we have three vector operators. This is a big jump now, but this is the basics of the electric fields. We have three vector operators that we use normally with the electric field calculations. One is rotation, we call. It's an external product of two vectors. And this is the operator, Nabla operator. It's a vector operator in this case. So it's a vector operator, we put an arrow on it. It's a vector operator. Then the external product is not a normal product. Are you aware of what is this? An external product in vector calculation? I hope so. Yeah. Otherwise, if you don't, please check. Yeah. Electric field, which is a vector. And we're going to, it's mentioned there that it's 0. Which it's possible like that, because the answer is the product is a vector again. We know that in field we work in AC, here the product should be 0. It's not always 0, but in the part that we focus on is 0. That's the first thing. I will get back to this, what it means, because it looks very simple, it is, but why do we need to know about it? The second one is the gradient. This is something that you should be familiar with, all of you. Electric field equals minus the gradient of U. There's a gradient in the potential and the voltage in the electric field. Okay? And the third one is the divergence. Vector operator, internal product. D. I jumped to another capital now. Y equals rho. So here you see, okay, we have vector operator on a vector, and you get a vector as an answer. Here you go from a scalar to a vector, and here internal product vector times vector gives you a scalar. These are the three possibilities. In fact, who knows what is D? Because E is the electric field. Yeah?
C times epsilon 0 times epsilon.
times R. Yeah, okay. That's a dielectric flux density. And okay, going to make it too difficult for you here. There's only a constant in between. In fact, there are two constants in between. Yeah. They both are vectors. What is epsilon 0? It's the permittivity of vacuum. Yeah. And epsilon r, the relative permittivity. So it really means as soon if we are in vacuum, vacuum insulation, for instance, epsilon r equals 1. Yeah. Which really means if epsilon r is 1, can epsilon r be smaller than 1? No, not in as far as we know right now. But, so epsilon r is always larger, equal or larger than 1. If epsilon r is larger than 1, what does it mean? It means that we no longer have vacuum, but apparently we have something that can be polarized, as we said. So in order to polarize something, we need to have molecules. Otherwise, so in vacuum, nothing is possible. So as soon as we have a real material, it can be a gas, or solid, or liquid, then epsilon r becomes larger than 1. Yeah? These three, rotation, gradient, and divergence, are of importance. Okay, let's first have a look at the first one. Okay, we take a point here. So this is our space, and we have an electric field in this room. In fact, we do have an electric field in this room, but that's another story. So we start here, and I integrate the electric field from here to the door here, and I go back to the point, the starting point, but then taking a different route. Yeah, can be like this. So here, I keep on integrating. Here, I come back here. And what is the result of this integration? 0. If we say in a curl-free field, and what does that mean? That there are no sources in the field, magnetic sources. Yeah? But what we are considering in this course, for what we are considering, this is true. And to express this in vector notation, you say a rotation of the electric field should be 0. You know, you can work with electric fields in vector notation and integral notation. Yeah? I hope you still remember that. Yeah? So the integral notation is the integral from here to there and back of electric field should be 0. You see that in the middle? No. But you can express that in the local quantities in the vector notation as nabla times E is 0. That's it. Really. Yeah? Yeah.
Where can I actually use this formula in actual events? I mean, where can I actually use it?
You will see that later when we're going to make use of Maxwell's equations. Yeah. You can I can give you one answer already now. Suppose you make this integration and you end up with something which is not 0. What can you say then? That there are some sources in your volume there. That's. Or if you know that there are some sources, and if you end up with 0, you know, that's okay. Sorry for the, I don't know. But then the second operator is the gradient. Okay. You should remember that the relation between electric field and potential is like minus the gradient of the voltage. Don't forget the minus. What does it mean for the direction of the electric field? If here I have a higher potential than there, how is the field directed? In the direction of decreasing potential. Yeah, that's directly the reason why we have a minus also. Yeah. And if we work in Cartesian coordinates in 3 directions, that's what we get. Yeah, so the electric field is a function of changes in potential in the x direction, and changes in the y, and changes in the z direction. It's all very straightforward. Huh? There's a nice analogy between. Do you see what it is, by the way?
Example of
Armando, is this Spain? No, huh?
Almost close to.
That's Portugal, in fact, Serra da Estrela. But what do we see here? What do we see? All these lines, what are they?
Altitude lines.
Altitude lines. Yeah? And if the altitude lines are close together, what does it mean? It's very steep. Yeah? Okay. So now forget about the altitude lines, and now we're going to call these lines equipotential lines. Lines where the potential is constant. Yeah? What does it mean? If the equal potential lines are close to each other, it means we have a high what? Electric field. So it's the same. Yeah? And for if you're going to hike in the mountains, this is very valuable information because in one glance you see where it's very steep. At least if you go from here to here, sometimes it's better to go from here to here. Yeah. If you want to analyze a design, insulation design, and you plot the equipotential lines in design, you can see directly where the stress, the electric field, is highest. So that's somewhere there in that area. This is how it's used. And the tools, remember the tools I mentioned before the break for shaping, grading the electric field. We use these tools for flattening the mountains, so to speak, make the whole picture less steep, or to move away the potential lines from each other, thus reducing the electric field. That's the analogy. I hope it helps. I don't know. It's just in my mind. Then the third operator of the electric field, which is really related to Gauss's law. Nobody asked me what this is. I explained what this is. What is rho?
Charge density.
Charge density, but just any charge density or
The volume.
sorry?
In the volume.
Yeah, but that's already volume. It's volume charge density. Yeah, but we always have charge.
It's the net,
Remember, we can
net
make.
charge.
Sorry.
It's the net charge.
You know, we have things like bound charge. Remember that? We make a distinction between bound charge and free charge. Does this ring some bell? Somebody? No? Okay. What is an example of a bound charge? You all know about polarization. Yeah. So if I have a system of you have dipoles, yeah, water, for instance, H2O. One part of the molecule is slightly more positive, the H part, than the other part slightly more negative. So you have an internal dipole there. So you can say we have plus and minus charge, but they are linked. You cannot move the negative charge independently from the positive charge. It doesn't work. So it's a system, bound charges, if you like. This is just one example of bound charge. Something else, if we, for instance, we shoot electrons with an electron gun into a system. These are free charges, there's no counterpart. You're more or less free to move, but more importantly, there's no counterpart there. So in that sense, they are net charges. Yeah. And this charge density, what do you think? Is this bound charge or free charge?
It's free charge.
It's free charge. Yeah, it's very important. Okay. How much to say about this? You know about Gauss's law. I'm not going to explain this or in terms of equations, but what is behind it? You consider a volume. You see there, a shoebox. Yeah. And you look at this volume here. There's a certain flux density D going in, and there's something going out. Yeah. The difference between the two, if what goes in equals what goes out, it means there's no charge inside this volume. If there's a difference between the flux going in and the flux going out, there's a net charge inside, which can be positive or negative. That's the very simple description in words. Yeah. You can think of a bucket, and you pour water in it. Initially, there's only water going in, so there's charge or water in this case inside the volume. At some point in time, all the extras are going out again, so then we have a stable situation, just like that. And that is what is related to what we call divergence. You have in different moments, you will see we will use the concept of divergence. For instance, in DC, I know I shouldn't talk about DC, but this is an easy one. You all know about the electric current. The electric current going into a volume is larger than the current that goes out. What happens inside? Charge builds up again, yeah, and the other way around. So that's what's behind. You will see a little bit later on, I guess already next week, why this, you should know about this and how you can use it. This one right here. Who remembers these two equations, Poisson's equation and Laplace's equation? If you raise your hand, I will not ask you to explain anything more. So nobody remembers.
I know what the relation is, but it's been a long time.
Okay. Again, to introduce in a simple way. I don't have my pointer here, but okay. Up there, nabla d equals rho. We've seen that. Yeah? One of these is the divergence of the flux density gives you the free charge. Okay, we can substitute the electric field there. So we get now epsilon times divergence of E equals charge density. If we add the relation between electric field and potential, E equals minus nabla U, we get minus epsilon nabla internal product nabla U equals rho, and then we get nabla square of U equals minus rho divided by epsilon. This is the general equation, yeah, which relates the potential distribution to a charge distribution. This is Poisson's equation. Sometimes there is no free charge, for instance in AC applications. It becomes simpler, and we get that one there. Nabla square U equals 0. That's Laplace's equation. Why bother about these things? Because you can calculate, if you know the properties of materials and the shape of a construction, by using these equations, you can calculate how the electric field or the potentials are distributed. It's an extremely simple relation. The implementation sometimes is not so simple, I agree. But this is what is behind something which is really nice and simple. So you can imagine in the other course on a high voltage DC, I can no longer assume that the end result is 0, because we will have free charges on the DC, but then we have to use Poisson's equation for our calculations. But the general form is this one.
Why aren't there free charges in AC?
That's quite a statement, huh? Yeah. Well, there can be, but maybe it's better to explain why you should expect free charge on the DC first. DC. We have an insulating material, let's say a capacitor, yeah, and the electric field is always in the same direction on the DC, yeah, because this is always plus, for instance, this is always negative, so electric field is always in this direction. So charge carriers, electrons, for instance, in the electrodes, they always experience a force in one direction, not only a force. So the electrons will have a force in this direction. It doesn't mean directly that they're going to jump from the electrode inside the insulating material. It's much more complex than that. But there's a tendency in one direction, movement of charges. Yeah. So charges can be, if the electric field is high enough, injected into the insulating material, and then they can move along through the insulating material, which sounds strange because this is an insulating material. But in real life, nothing is perfect, so there's no such thing as perfect insulation. So even in an insulator, charges can migrate, sometimes very, very slowly, but it's there. Under AC, let's say 50 Hertz, the field flips 20 or every 10 milliseconds. Yeah? So there will be no net injection of charge carriers because in one phase they're injected, the other way they are extracted again. So usually there's no net effect. I must be careful because if we go to ultra high voltage AC applications, the fields become very, very high, and then there can be an imbalance between injection and extraction. But this would go too fast. Sometimes I have to simplify things. So in principle here for AC, no free charges. For this reason, and on the DC you have to expect free charges. Sometimes I need to simplify because there's so many buts and ifs, and that would not help you right now. Okay? But the question is very valid. Okay, before we part, so we're close to 5:30. There are two concepts that are essential in this area, which are one already introduced: equipotential lines, lines with equal potential, constant potential, and field lines. What is a field line? One way of explaining it is, let's suppose there's an electric field inside here. I would position an electron here. What would the electron do? It would experience a force due to the electric field. Yeah? F equals the charge times the electric field. But the field is in a direction, so the force is also in that direction. And the electron would follow the electric field line. So it's a way of telling you what is an electric field line. Or it would follow a decline or an increase in potential. It would go uphill, so to speak, the electron. Yeah. So that's why it says the field line represents the path that a small positive charge, now not a negative, but a positive charge, would follow if it were free to move in an electric field. The electric field is in this direction, positive charge would move in this direction. Usually we talk about the electrons, and that's why we see the minus all the time in this form. There's something involved there, which is very important. A field line cannot cross an equipotential line at an angle other than 90 degrees. This is quite a statement. I can tell it's true, it's not a trick, but